first of all, I'd like to thank the members of the Academy for the invitation. It's really an honor to be here, a privilege. And of course, I should congratulate Douglas, Connie, and Jörn, and also to thank them for laying the groundwork that made most of the exciting science we're discussing today possible. So my contribution today is going to focus primarily on one application of seismology, which is to use constraints on stars to learn about the assembly history and the evolution of the Milky Way. Now, when we think about pulsating stars as traces of populations of stars in the Milky Way, we need to take a step back to, I would say, a little bit more than 100 years ago, because then in 1908, Henrietta Leavitt showed that actually pulsating stars, in that case primarily Cepheids, can be used as distance indicators, as cosmic yardsticks. And this is what really meant a step change in our understanding just of the scale of the galaxy itself and the universe. And in terms of information we can get from pulsation modes, even if we stick to a fundamental mode, a radial mode, just 10 years later, that pioneering work of Leavitt, then Eddington published a paper saying very clearly that, say, if we have two stars or two spheres of self-gravitating gas, then the periods of oscillation, thinking about the fundamental mode, would be inversely proportional to the square root of the density, of the mean density. And that already opened up or made it very clear which kind of information we can potentially retrieve from oscillation, so a combination, I would say, of mass and radius. Whereby the radius, of course, you can use it, if you manage to determine that very precisely, to size up the propagation cavity, and then use it, again, as a yardstick, if you like. And then the mass, it's a little bit less evident, but for stars that are in an evolved phase, such as giants, such as Cepheids, and Aralaria stars, one can use the mass as a very good proxy for its age, which is basically what I will be talking about. But then, in terms of information that even let's say, a fundamental mode can give us, there's a lot more than just the mean density. And in a paper in 41, Paul Ledoux and Picaris showed very clearly and quantitatively that if you have stars that are non-homologous, then the fundamental mode, its period, would scale as the square roots also of the moment of inertia. So meaning that if you have structures, we've heard today about red giants in different evolutionary stages. If we have a structure of a star which is more, let's say, centrally concentrated with a different mass distribution, for instance, then you would have frequencies which will be different even if the mass and the radius are the same. So this is just to show that, of course, there's much more information just even in one radial mode. And to some extent, these considerations is what we are basing most of the inference we're doing today. Now, going back to Cepheids, or classical Cepheids and Aralaria, these stars can be used not only as distance indicators, but they are also used as traces of, let's say, the young, where by young I mean stars or population about, let's say, 200, 300 mega years, so not as young as the massive stars, of course. Or for Aralaria of, let's say, the old population, where by old we mean a population which has ages comparable with globular clusters, primarily because Aralaria were and are observed in globular clusters. Now, in this plot, what I'm showing is a very simple relation which you expect from sort of basic stellar evolution, and it's that for evolved stars in the giant branches, we expect, as I was saying earlier on, a very tight correlation between the mass of a star and its age. And being able to infer the mass of stars with seismology is really what is giving us the ability to measure ages. But here, as you see, we have strong limitations. On the one hand, there's a big gap between a few 100 million years and 10 giga-years. And also, as I was saying, the precision with which we can infer or estimate ages doesn't really go much further than saying the old population. But of course, we need much higher precision to be able to use the information then to contribute to understanding the evolution of the Milky Way itself. So in this context, and that's where the detection of solar-like oscillations in giant stars made a huge change and a step forward. And here you're seeing basically the same plot as before. This is a synthetic population of giant stars in, say, red and yellow, just to show the correlation that we have, as I was saying, between the mass and the age of stars. The effect of metallicity is represented by color here. And the change with this detection of solar-like oscillation was, on the one hand, quite obvious. We can fill the gap between Cepheids and Aralaria stars. but also that the precision with which we can infer masses is of the order of few percent, meaning a precision, I'm not talking about accuracy yet, but precision that we can get on age can be as low as 10%. And the possibility of getting ages to 10% is really what is needed to make a sort of a step forward in understanding the assembly history and evolution of the Milky Way. So in general, if, say, the aim in general is to try and understand the evolution and formation of galaxies, one can tackle and should tackle this problem following different paths. So on the one hand, one can come up with, say, large-scale ab initio simulations of the universe in the cosmological context and get to scales as small as galaxies or populations of stars within galaxies. On the other hand, one can observe objects at high redshift. We've all seen the exceptional results we're getting from JWST or ALMA, where we can see that disk galaxies are present already at relatively high Z, so very early in the history of the universe. But then a complementary approach is that to look in our, say, back garden, if you like, so looking at the detailed properties of stars within our own Milky Way. And the idea there is to use these stars as fossils, so to be able then to reconstruct, say, the timeline of events that led to the Milky Way to what it is now and that we can observe. And so to play this game, we need lots of data, complementary data, starting from the position and parallaxes, or the distance of stars, and that, thanks to Gaia, it's something we have for a large number of stars with very high precision, and also the proper motions that, coupled to radial velocities, then can give us information about the full six-dimensional phase space. And then, of course, we can couple that with information about the chemical composition, at least the chemical composition of the photosphere of stars. And this is wonderful. We are very, lucky to live in an era where these data are, available. And I guess astronomers have been waiting for this kind of data for many, many decades. So this is all great, and we can use that to have a incredibly detailed picture of stars in the galaxy right now. But of course, the aim is to go beyond that and is to try to reconstruct, again, a chronological sequence of events that shaped the Milky Way to what we see now. And that's where the role of seismology becomes quite important in determining ages with very high precision and improved accuracy. Now, in this context, and now I think it's quite well recognized by the wider community, seismology, especially of red giant stars, which are intrinsically luminous, so they span long distances away from us, they provide the way forward. Why? Because with seismology, we can get to masses which are, say, few percent, with uncertainties of few percent, and so getting their ages. The way we do that, well, there's several layers of complication, different approaches, which I'm not going to discuss in detail now. Let's say, in general, one can take a power spectrum. This is a power spectrum of a red giant branch star, measure some global properties of that spectrum, and use that in comparison with prediction from models to infer ages, and typically one gets an uncertainty of about 20–30%. And then there is also a more, say, ambitious approach, which is that of starting to use the information that is carried by these tens of individual mode frequencies, and then again compare these frequencies with prediction from models and use that to constrain the ages. And that's how we can get to this 10% precision. And now the sort of, let's say, journey of trying to including seismic constraints to then learn about the evolution of the Milky Way started already 15 years ago, and thanks to initially to the detection of solar-like oscillation with Corot, which was a French-led mission, and in 2009 Joris and Saskia published the first detections, but the detections were not one or two stars. We had thousands, 1,500 stars, if I remember well, in the first two runs of Corot. And that's where we realized that looking just at the distribution of these average parameters, those distribution had or carried the information about the radius of those stars and the radius distribution, which we could use to determine distances, but also, more importantly, the mass distribution, which is then a proxy for the age. And so then, when a few more tests of these seismically inferred masses and radii were available, then we tried to push this work a little bit further, comparing the population in two different fields observed by Corot, and what we could see was a difference in the mass distribution, which we believed came from basically the vertical age gradient in the Milky Way, so looking at actually a field which was basically on the galactic plane and a field which was further away. And along the process, what also had to happen, and which was by far the most enriching part of the journey, was that to try to define a direction where to push and to advance, we had to sit down with different experts in stellar evolution, seismology, but also in spectroscopy, in chemodynamical models of the Milky Way. So that took time and convincing, of course. But then, and then also what happens, other than convincing people and interacting with people, is just that many more data became available. So just to show you what changed in the last, again, 15 years, we started with Corot. So all we knew about Corot targets was what we had in that plot there, so just a color magnitude diagram, but the magnitude is the apparent magnitude. We had no parallaxes from Gaia. And so it was even very difficult to discriminate giant stars from dwarf stars. But this is also what saved us, because people who were selecting targets for Corot, they didn't really know how to get rid of giants. So that's why we got thousands of giants in Corot, and we shouldn't forget that. But then things change, and now, for instance, with Kepler, we can plot a Hertzsprung-Russell diagram where we have luminosity based on Gaia parallaxes. We have effective temperatures from spectroscopy. We have an information on the mass that comes from seismology. So you can see this beautiful diagram where you could recognize all the sort of known features in the giant branches, the bump, the red clump where stars that go through a helium flash burn helium in their cores, then the secondary clump, the vertical structure. This is really a playground for stellar physics. So there's a lot of open questions, long-standing questions that one can recast with this the availability of this data and try to reply to them. But not only that, for each of these dots that you see in the diagram there, we have available orbital parameters from Gaia. We have available photospheric chemical composition thanks to spectroscopic surveys. And even more importantly, as Saskia illustrated earlier on, we have available very detailed picture of their internal structure. We can very easily discriminate between evolutionary phases, for instance. This is very important, of course. Now, having all this data, we also had I would say, the possibility of having observations not only in the Kepler field, but then also in quite a few different fields with K2, so the repurposed Kepler mission, so exploring different areas of the Milky Way. Of course, TESS is still collecting a lot of data, although, of course, the quality of the data is significantly worse than that of Kepler, but still we can start studying different populations in the Milky Way. And so then, when we started to put together these data, there were a few papers that appeared, for instance, a paper by Casagrande using photometric data and starting to see, I guess, this vertical age gradient in the Kepler field. Then a paper led by Sylvain Aguirre, where they could clearly see this dichotomy somehow in the age distribution of low alpha stars and high alpha stars. And then adding also constraints from Gaia and increasing the size and the precision, size of the sample and the precision in the ages, then we could look at, for instance, the top plot, the age-metallicity relation, showing very clearly, for instance, how the Fe over H distribution gets wider as age increases. And this, we believe, for stars that are actually located at the solar galactocentric radii, is the evidence that indeed there are dynamical processes that can transport stars and move stars from different orbits and with different angular momenta, so bringing basically old metal-rich stars from the inner disk up to the solar radius. And also we had a few hundred high-alpha stars for which we could determine the intrinsic age spreads, meaning that, for instance, we found that say 95% of the population there had to be born within 1.5 gigayears. And the possibility of adding Gaia constraints on the orbital parameters also led us, for instance, to understand and characterize the age-velocity dispersion relation and find a significant difference between that relation for low alpha stars, where you can see in the bottom plot there, we can see with age an increased vertical velocity dispersion, which we can relate to dynamical heating of the thin disk. On the other end, we see the high alpha stars, they are on a different level there. So this is suggesting again that what we may call, or some may call, the thick disk was not formed, or its dispersion in velocity by a secular process, but from an event, could be a merger or a strong accretion in the early phases of the Milky Way. And also one can start, for instance, inferring radial metallicity gradients. You see here a paper based on Corot data. Now there's more based on K2. And if you start from the panel on the left, the upper panel there, you see the Fe over H gradient, a gradient with respect to galactocentric radius. And you see that the blue points, which are stars for which we had ages from Corot, they actually give a very similar information to what Cepheids already could give. So that was a sort of a sanity check to some extent. But then, of course, we could extend the age range to all the stars. And we could see, for instance, not only a flattening of the gradient, but also an increased dispersion, which, as I was saying earlier on, then one could and should quantitatively compare with models of dynamical evolution and radial migration. Now, in terms of pushing to the extreme to some extent, what we've also tried to do in the community in general is to try and get the ages for the older stars, which is, of course, the hardest thing to do, because for a star that is 10 giga-year old, we need to have a resolution of about a giga-year to hope to be able to set a sort of timeline of events, so at least in terms of relative ages. But we were lucky enough that among the stars in the Kepler field, we had a few stars that belonged to the so-called Gaia Enceladus galaxy. That is a dwarf galaxy that people think was accreted by the Milky Way early on. And then we could have this comparison and determine ages using individual mode frequency and show, for instance, that a significant fraction of the in situ stars that were born in the Milky Way disk are actually older than stars in the Gaia Enceladus. So that can help us, again, trying to set a sort of timeline of events that shaped the Milky Way early on. And yeah, just as a short interlude, I'm going to see if that works. I'm just going to play the acoustic spectrum of one of these stars originating from Gaia Enceladus. If it works, probably doesn't. Let's see. No, okay, sorry. I thought it would be good to at least play for once the acoustic spectrum, but that's too bad. Anyway, as Douglas was saying this morning, it's definitely not a musical instrument. It's not a pleasant sound, so it's probably best this way. Anyway, so just going back to determining ages. Of course, we're all excited about this precision, but there's a key question to be asked: is what is the accuracy of this determination? And there's a lot of efforts that within the community we are putting in finding calibrators where we have independent measurements of mass, basically. And this is hard. It is hard because we need masses determined to a few percent or 1% to be able to challenge seismic masses. But we have the luxury of having few clusters, unfortunately only open clusters in Kepler. But the prime, I would say, calibrators are detached eclipsing binaries, and I'm really happy to say that now we're getting, for some systems, to a precision in mass and an accuracy, in the case of eclipsing binaries, of the order of 1%. So we can finally challenge seismology to that level. And then, of course, also Gaia parallaxes are really, really important in testing the determination of radius with seismology, which, as we know, is strongly correlated with mass. So any systematics we see there can be indicative of an issue we have in the mass and then in the age. Now, and as a sort of final example, while you try and determine the ages for 20,000 stars, sometimes you find very unusual or unexpected values. This was the case for a few stars in the Kepler field, where we had stars with estimated ages of around 30 billion years. So what do we do with those? And it turns out there's a few stars, especially those red crosses that you see, or red stars actually there, that are basically hiding in plain sight among many other giants. But these stars are in the core helium burning phase, but have a mass that are like around 0.7 solar masses. So what's going on with them? And do we actually believe the mass? So what we did, that was work done by a PhD student in Bologna, is to model those stars. And then so we have stars that have, they say, the canonical helium core mass of 0.47 solar masses, but have an envelope which has to be 0.2, 0.3 solar masses. And those stars, when you model them, you expect from the propagation diagrams, what we've seen a few today, that basically what happens in those stars is that the G-mode cavity that resides in the sort of inner radiative core and the P-mode cavity are very strongly coupled together, because this evanescent region is extremely small. And in that case, what we expect in the spectra is to see basically mixed modes all over the place, which is indeed what we see in this spectra in the bottom part. So what may look noise to some people, these are actually just a forest of G modes, or actually mixed modes, that populates entirely the spectrum. So we do understand quite well the structure of these stars, and it's important that we have a signature to identify them. Of course, no one believes 30 gig a year, but there could be cases where the age is reasonable, but still the structure of the star tells us that these are most likely products of binary interaction, to go back to also the presentation by you. So there's a lot of interest now and a lot of work from different people trying, on the one hand, again, to characterize this structure, their internal rotation, for instance, but also then to come up with a scenario involving binary evolution that can explain the occurrence of these stars. There's also a star in a cluster in Kepler which has this signature. So this is, I thought I would show this just as an example, that the sort of detailed understanding of stellar structure, evolution, also of binary evolution, is necessarily very strongly connected to our efforts in determining ages. This has to be necessarily the case. So that brings me to the summary. Pulsating stars, as I said, have been an asset to understanding the structure of the Milky Way since more than 100 years. Initially, with thinking about Cepheids and RLI, the main contribution was to use them to infer the distance scale, and it is still these days, of course. But with seismology, I think the contribution that is really key now is that solar-like oscillation, or these giants, they're really helping setting the age scale, which is as important, I would say, as the distance scales. And because that, with a 10% precision and hopefully accuracy at some point, we can really use these stars to link, let's say, local fossils, so stars in the Milky Way, to what we see at high redshift with, say, James Webb. And on the other hand, of course, the age uncertainties are dominated by the systematic effects related to our limited understanding of stellar models. And we know that the details of the models can change significantly the oscillation frequency. So depending on which category you want to be, you can see that there's a limitation to the accuracy, of course, in age. On the other hand, we know that the information on the details of the models is there. So the hope is that when we will be able to perform these tests, especially in clusters, in controlled environments, that's where we can really pin down the physics. So just making the point that the development and testing of models is necessarily intertwined with the inference on age. And just want to conclude by thanking the many collaborators I have the chance to be working with, and again to thank Douglas, Johan, and Connie also for being an inspiration. Thank you.